Okay, AP Physics, here we go. Now, Chapter 16, if you're great at reading the book, you can read the book, you can get this information. I think that's important that you should be able to do that, but I'm also giving you another alternative resource, and that's to follow me along. I'm going to cover a couple sections from Chapter 16, a lot of which we already covered or talked about, but in the future this won't be that way. This will be where you'll get your information on a particular chapter. So we talked about electric charge this morning, and we're going to continue on with that. So the key things is that the charge comes from the movement of electrons, and you can have static charge, and that's what I showed you this morning, where you have a charge that's not moving. Once you built it up on some object such as the balloon, then that charge did not move anywhere. Key thing to know about that static charge buildup that you saw in that balloon was that the net amount of electric charge produced in any process is zero. So in other words, you didn't produce any charge, you just moved it. So the balloon gained a bunch of charge, and therefore my sweater lost charge. And so the net change, the amount of electric charge produced, is still zero. Okay, so net charge in any creation of static is equal to zero. That makes pretty good sense, I think, if you think about that. So what you gain from somewhere, you had to lose from somewhere else. So a couple things that we want to talk about. I had you mention that rubber was a good insulator, so it didn't allow the charge to migrate over the surface of the balloon. It sort of kept it in one area. So two key things: insulators. Oh, sorry, I pulled that. That should be insulators, and conductors. So if you think about insulator, insulates the migration of charge from one point to another, and a conductor is very good at conducting that charge from one point to another. Great example would be if I took two balloons. Here's a balloon and it's full of negative charge. Those are indications of negative. The size does not make a difference in the charge. Or I'm sorry, let's make that not a balloon, but a metal sphere. So we got this metal sphere, and it's negatively charged. And we got this metal sphere, and it's neutral, let's just say. So this is charged, this one's charged, and this one's over on the right is neutral. And if I take a metal rod and put it over the top and let it touch those metal spheres, then what we'll get is a migration of charge over to this. And then if you move the rod away, you would then you could then have both of them having a slightly negative charge. So, you know, if this had excess charge, so some of the charge would migrate over, and that's sort of indicative of a conductor. Whereas if I put a piece of styrofoam over that, if I change this metal with styrofoam, now I replace it with styrofoam, guess what would happen? Nothing. It would just stay there. So that's pretty simple to understand. And you could also sort of do that with positive charge. If one was charged positively, and so it had a loss, net a negative amount of electrons compared to, or less electrons than protons, then you could get a migration of some of the electrons over to where both spheres could become positively charged. And that's pretty simple. Okay. Imagine you could induce a charge. You saw me this morning with the balloon and the pieces of tape. So imagine if you had this metal rod, for instance, and you brought that balloon. Here's the balloon, and you brought the balloon. Here's the little tie, and it was negatively charged like it was this morning. And you brought it up close to this metal rod. So this is metal, and this is the balloon without. So if you bring it up close to the metal, then it's going to push the electrons over to this side, to the right-hand side. And then this side will become slightly positive. Sort of like, that's sort of what I explained to you as to why the balloon can stick to the wall. Now, you didn't touch the metal, but now imagine if you were to now just sever somehow, magically, or just quickly, this rod. So just like I did, I severed it right in half. So now we've induced a charge into this rod where this side, the right side, equals a negative, and the left side equals a positive charge. So we've induced a charge into that rod without even touching it. And then we knew we saw charging by friction as well. There's a couple things that I want you to be aware of that are pretty good detectors of charge, and that's an electroscope. And that's it sort of shows charge. Pretty simple little device. And I've got a couple that you're going to have to work with and just sort of familiarize yourself with because they're pretty interesting. And it's a metal rod going down through this, and this is glass. This box is made out of glass, and it has two little leaves on it. I need to go back on that leaf. Leaves made out of gold, very thin leaves. You remember how we saw making of gold leaf? Anyway, if you bring a charge into this vicinity right here, if it's negatively charged, it's going to push the electrons down to where these leaves become negative, and of course then you would see them, and I'll put this in a different color, you would see them push away from each other. Those leaves, those gold leaves would push away. That's the yellow that you see there on your screen is that after they become charged, and so they're pushing away from each other, showing a charge. The same could be true if you could induce it to become positive. So if both of the leaves became positively charged, then they would push away as well. All right. So then we got to Coulomb's law, and in Coulomb's law, we wanted to just okay, so getting back to Coulomb's law again here, just was catching my thoughts. So I already gave you that, and we showed, I got to go back to that nice color, nice, more contrast with the white. F equals K Q1 Q2 over R squared. Very similar to the universal law of gravitation, as it should be, because this is a field force. And field forces are pretty weird things, so gravity is a field force. This electric force from the static charge is a field force. That means action at a distance. Doesn't have to be in contact with it, and it can exert a force upon an object. And this equation is helping you discover that force that can be exerted upon another charge. If you bring a quantity of charge in the presence of another charge, then it will exert a force on it, and this is going to help you determine that. So that's the abstract thing, I think, in this case, is what is that other charge? Where is it? How do you create just an amount of another charge? But we're going to deal with it in that magnitude here today. Just bringing two charges close to each other, maybe three charges close to each other, and see how they work with each other. So the simplest case is you have an x-axis like this. Let's make that our x equals 0. And you put a charge here at x equal maybe negative 3. So we'll put and units are just in standard whatever units you want. And so we put one at negative 3 units along there, and let's just give it a charge of q. And then we put another one at 3 units, and it'll be a charge of q. So as you can see, we could, if we wanted to know the force that exists between here, then we would talk about that K, that constant I talked to you about, Coulomb's constant, 9.0 times 10 to the 9th newtons times meter squared over Coulomb squared, times Q1, we'll call that Q1, doesn't matter which one you call Q1, Q2, over the radius between them, or the distance between them in this case, squared. So that would be 6 in this case, right? There would be 6 units of distance between them. So that's really it for Coulomb's law. So what makes it so hard is just that you have to do the superposition sort of problem here, and that what happens if you have an x, let's just put an arrangement together like this. So here's in 2 dimensions. So you have a charge at the origin, we'll call that one plus q, one here and along the positive y-axis, and we'll make that one negative q, and then another charge here along the positive x-axis, and we'll make this one plus q. And so let's just say that we want to find the net force acting on, let's see, charge 1, Q1 Q1, we're going to run a little bit over 10 minutes. I'll try to get done here in about 11 minutes or so. Q2 and Q3. I mean, not 11 minutes total, but just 11 minutes. So Q1, Q2, and Q3. So let's say we want to find the net charge on Q3. So let's think about that. Well, let's look at this force pair relationship here. All right. So Q1 is going to pull on Q3 because they're oppositely charged. And so like charges repel, opposite charges attract. So it's going to pull on Q3. So we can, let me get rid of that arrow. There we go. And let's make it better. So here we go. So that Q1 is going to pull it this way. And then Q2 and Q3, well, oh, just by the way, Newton's third law applies here. So Q3 will pull on Q1 equally. But remember, as in all free body diagrams, we only want the forces acting on the object. And in this case, the object is charged Q3. So Q2, let's see, like charges come relative to Q3. We don't care about Q1, Q2, because we're not asking for that. With Q2 to Q3, Q2, there's a pair, so we could apply Coulomb's law there, and that's going to push Q3 away. I don't know the magnitude. I don't know if these vectors are to magnitude or anything. I'm just pointing out the direction. And so there we have a little diagram, a vector diagram, and as you can see, that's going to become a bit of a classic add vectors not at right angles. And so what would we have to do? Well, we would have to then find for this vector, which we'll call Q1 on Q3, we'd have to find this component of its force and this component of its force. And then for this vector over here, which we'll call Q2 on Q3, well, heck, it's right along the x-axis. So as we know, it does not have a y. Well, it does have a y, and it's 0. So anyway, so we would then add these two together and get their resultant, and then we would add them to the y, and we'd have some final x and y pair, which we could find the magnitude. And, you know, that's just like we did back at the beginning of the year. So that's what I like about this, is just that it's actually reinforcing the concept of vector addition that you learned so long ago and that we did with free body diagrams and the applications of Newton's laws. So I am going to stop right there with 12 minutes and 40 seconds or so into this video, or I don't know if you call these videos, but through my AP Physics class, I think you will understand what we're talking about. So make sure you look at this with the book, and while, you know, either before or after, but it'll help you out. All right, that's it for the day.